it on? All right, let's get started. Hello, everyone. Welcome to this session for class and other things. So my name is Ying. I'm from University of Utah, and I will be the chair of this session. And in this session, we are going to see 6 wonderful papers about ThinkShare and class simulation. And the very first paper that we are going to study, the title is Physics-Inspired Estimation of Optimal Class Mass Resolution, and authors are Diyang Zhang, Zhendong Wang, Ze Gaoliu, Xinming Pei, Weiwei Xu, Huaming Wang, and Zhendong will be the presenter. Let's get started.
Okay, thanks for the introduction. Good afternoon, everyone. My name is Zhendong Wang. I'm a senior researcher at Stat3D Research. Today, I'm excited to present our work on physics-inspired estimation of optimal close mesh resolution. So, the first motivation behind our method is quite straightforward. Let's take this laser jacket for example. Because laser has relatively high bending stiffness, we only see coarse wrinkles in this jacket. So a lower resolution mesh is sufficient for simulating it. On the other hand, silk fabric is much softer and tends to generate fine wrinkles, which means it requires a higher resolution mesh to capture fine details accurately. Another key motivation is that simulation accuracy tends to plateau once mesh resolution goes beyond a critical point. In other words, increasing the mesh resolution further doesn't always lead to the noticeable accuracy improvements. It just adds more computation. To verify our findings, we did a cantilever test on a piece of cloth using different mesh resolutions. As shown by the side curves, once the mesh resolution drops below 6.5 millimeters, the simulation results barely change. So in this case, 6.5 millimeters can be considered as the optimal mesh resolution for simulating this fabric. Okay, this makes a key questions. So can we estimate the optimal mesh resolution for a fabric without having to run trial simulations? Our answer is yes. So our first key idea is to use experimental wrinkle physics to compute optimal mesh resolutions by taking into account both material stiffness and the garment-specific boundary conditions. Since wrinkle patterns may vary across the fabric and do so anisotropically, use a uniform mesh resolution is inefficient. Our second key idea is to apply the concept of wrinkle transition distance from experiments, which helps us smoothly transition between regions with different resolutions. Okay, let's see the first experimental wrinkle theory that our method builds on. This theory describes the characteristic wrinkle wavelengths in thin materials. In a basic stretching experiment, the first formula tells us that the characteristic wrinkle wavelength is proportional to the fourth root of the ratio between bending stiffness and the elastic stiffness. And the second formula shows that the wrinkle attitude is proportional to wavelength and the square root of the compressive strain. Finally, the third formula relates elastic stiffness to the fabric's Young's to materials Young's modulus, where the function f plays a key role in capturing the geometry of thin materials. So we can define the optimal mesh resolution for representing a sine wave according to the Pythagorean theorem. Since the optimal resolution is proportional to the characteristic wavelength and the geometric function f can be expanded by 2 constant parameters, C1 and C2. So we got a sixth-order polynomial equation. The constant C1 and C2 can be determined based on the limits of mesh resolution and material stiffness. Okay, let's see some results. Once C1 and C2 are computed, we can, using a fabric expanding stiffness and its Young's modulus to calculate its optimal resolution in our simulation system. When using overly coarse resolutions, the results can differ significantly from high-resolution simulation results. But with our estimated mesh resolution, we can closely match the final results while using much less computational resources. For anisotropic fabrics, we estimate the mesh resolution separately for the weft and waft directions. So this helps us prevent the mesh from overly dense in one direction while staying efficient and accurate overall. The second experimental wrinkle theory that our method builds on is about how wrinkle wavelengths propagate. In the wrinkle experiment, the first formula shows that a characteristic wrinkle wavelength grows with distance and follows a power law relationship. Specifically, it is proportional to the distance raised to the power of m. The second formula describes how far you need to go for a wrinkle wavelength to double. It says this distance is proportional to square root of the original wavelength and the square root of the ratio between the boundary tension and the bending stiffness. In our method for mesh resolution propagation, we assume that the resolution increases with distance and also follows a power law relationship. So specifically, the power parameter m is calculated as the logarithm of the resolution ratio divided by the logarithm of the transition distance. This means that given a boundary resolution Rb, the resolution at a distance x from the boundary is Rb plus x over power m. Where when there are multiple boundaries, we take a conservative approach and use the minimum resolution value at each point to ensure accuracy. So we also take into account some fabric techniques like shearing, folding, stitching, and downfilling, which introduce localized stress into a fabric. So given a piece of fabric with specific boundary conditions, we compute the resolution on the boundary using technique-specific rules. Then we create a smooth transition between the fabric's base resolution and the boundary resolutions to generate a continuous sizing map. So by using this sizing map, we apply Poisson sampling and Delaunay triangulation to generate the final mesh. The mesh assigns high resolutions to place where detail is needed and keeping it coarser as well for efficiency. Okay, let's see some results. This example shows that a smooth transition between fabric resolution and the boundary resolution can accurately produce better wrinkle details than using a uniform fine fabric resolution. And this is an example of folding, and this is an example of stitching, where a long edge is sewn to a short edge, causing wrinkles to form along the seam. And here is an example of downfilling. By taking pressure effect into account during resolution transition, our method creates a nice effect on down fabrics. And this is an example of multi-layer clothes with complex collision. Even though our estimated resolution is much coarser than the fine ones, it still gives nearly the same simulation accuracy. Okay, we also applied our method to the stretching test to verify that the first wrinkle theory on wrinkle wavelengths. Our estimated resolution of 3.8 millimeters produced almost the same number of wrinkles as the fine resolution of 2.5 millimeters. We also applied our method to a curtain test to demonstrate that the resolution transition matches the measured wrinkle wavelengths. Okay, for some comparisons, our method uses an estimate of optimal resolution of 7.83 millimeters which produce animation results similar to the fine simulation at 5 millimeters, but with lower computational cost. In contrast, dynamic reimagining not only introduces visual artifacts, but also requires more computational resources. This is an example of address with multiple shearing lines compared to the full simulation with resolution of 2.5 millimeters. Our method produces the same wrinkle effects while using much less computational resources. We have also tested our method on several other complex garments. For performance, as compared to the full simulation at 2.5 millimeters, our method is about 2 to 10 times faster, with a significantly reduced vertex count and minimal loss in accuracy. So because our method predicts the mesh resolution before the simulation, it doesn't fully account for complex dynamic collisions. So for instance, when the air ball bends and really compresses the sleeve, we can only handle it by labeling high collision area in advance. This remains a limitation of our method. So to conclude, our method proves that it is possible to estimate optimal close mesh resolution before running the simulation. However, dynamic collisions are still a challenge. So one of our future directions is using learning-based approaches to predict collision-prone areas. Okay, thank you so much for listening.